Hi, my name is Nick Hanousek. Thanks for having me here at the 5th Joules Physics Users Workshop. And today I'm going to be talking to you about what we've been doing, which is using SPH modeling to complement flume study in the development of a novel turbine design. My talk today will take you through the design concepts of the turbine itself, why we felt that SPH would be a good research tool to assess the design, a roadmap to the model within Joules Physics, some of the research questions that we've looked at and tried to answer, and then finally a view to the future. The turbine itself is known as Carbine, a truncation of Cardiff turbine, developed here at Cardiff University. The turbine is a vertical axis turbine inspired by Savonius turbines with a scalable design for use in a variety of situations. The way it works is that there is a body with a central axis and two large plates at the top and bottom, between which are held a series of flaps. These are hinged at one end, allowing them to rotate freely within the flow. When they are traveling downstream, they are pushed such that they align perpendicular to the flow, increasing their drag. And when returning upstream against the flow, they fold away so that their drag is reduced. For a more complete description of how this works and some performance benchmarks, I would direct you to this paper by Tom Harries, which is very good. So previous studies have consisted of flume-based tests, as pictured here, and CFD tests, which were done using ANSYS CFX in a pseudo-transient mode. These, of course, have their limitations. In terms of flume tests, the lab time and availability of technicians and component fabrications have been, limits the amount of changes that you can make within a short space of time. And when modeling in ANSYS CFX, I believe that the system is held as partially fixed, which we felt might not truly reflect the behavioral pattern of the carbine. So for this, we moved to SPH, where we can model the turbine as a series of components linked together in an accurate representative way. The first model that I put together was in Joules Physics, which took inspiration from a couple of the previous or the example cases, that of the current hull and the water wheel, which allowed me to use the chrono hinges to link the body to the domain and the flaps to the body. The flow speed was set at 0.9 meters per second with an initial depth of 0.2 meters, uniform at both ends, and all the parts loaded as STL files. This model proved functional, but rather slow. And for the amount of computational time, we felt that perhaps we didn't quite get the data that we required, since to properly model some of the turbine details, you need roughly millimetric resolution. And to have a full-sized accurate flume, you need obviously a much larger space. So to try and combat this, we moved to looking at 2D models. In this case, a sort of semi-depth averaged model, two-dimensional in the XZ plane, and the gravity set to 0 meters per second squared in all directions. This allows us to take a section view through the turbine, with my proof of concept being a more simple Savonius turbine. This does remove some vertical effects, which, although definitely important, did appear to be causing some instabilities of the turbine behavior, and obviously allows for far quicker simulations, allowing us to do more tests within a similar amount of time. The initial, or the majority of the testing that I've done to this stage has been on the startup behavior, where we see the turbine in an initially stationary position, and then under the motion of the flow, it begins to turn. And as you can see, the flaps here do rotate into position as expected, and the turbine turns. Currently, we have not been applying a restriction to the movement, the turbine could be viewed as free spinning, freewheeling. This is something that we intend to include in the future, but that for this stage we went without to keep things as simple as possible. The first question that we needed to answer was, are these tests reliable? So to do that, we quite simply ran the same test 5 times, shown here in terms of just the blades on the left, and the time series of the rotational velocity divided by the fluid velocity. And it's quite visible through both that for the first 1 to 2 seconds, the behavior is very uniform, it's very reliable. And as we move forward, small random differences steadily increase. However, the overall behavior of the turbine still operates within the same speed zone, and as such, and the periodicity is broadly maintained. So in terms of performance, we think it's enough to get some meaningful results from. One of the design concepts or target destinations for this model is for use as a singular power source or singular unit to be used as a power source for a remote or isolated community. This could be installed in a small stream or river and provide power to a place that did not have power. To test the resilience of this turbine, I felt that it would be important to see how it would respond to the loss of various arms. Because if this was being operated on a large commercial scale, replacing an arm would be relatively simple or trivial. But if in an isolated location, that process would take significantly more time, and knowing which arms are more important to the operation of the turbine and how they would affect it was found important. So to do this, I removed all various combinations of 1 to 2 arms from this base model and found that the results indicated that different arms do have different importances. If we look, for example, at the single arm missing case, you could either lose an exterior or an interior arm. And in this case, as one might expect, the exterior arm is more important because it causes the turbine to drop out of the sort of optimal zone at a couple of points. And that would lead us to believe that if you have one of these turbines and you lose an outside arm, it could be beneficial to move an interior arm to the outside position, and as such, retain slightly more of your power generating potential. Looking at the 2 worst case scenarios, the loss of both outside or 2 outside arms or an outside arm and then the subsequent inner arm caused the biggest losses in performance, where you can see here that the turbine is oscillating positively and negatively, and that's basically rocking back and forth as opposed to spinning, which again shows to us that the outer arm is more important, and that if you lose multiple arms, try to preserve those arms. Finally, as we know, the natural flows tend not to be as consistent as nice lab-based or CFD simulations. So we ran a series of tests at different flow velocities to determine the optimal, or at least the stages of flow speed where the model or the turbine can operate. From this, you can see that above 0.7 meters per second flow or so, the turbine will not fail out and stop rotating, which gives us a nice knowledge that below that it's probably not worth even turning it on, and allows you to more accurately determine what the potential locations would be. As we look to the future, one thing that I would like to look at is how different combinations of arms and flaps perform. As you can see here, we've got an option on the left with 3 arms, each with a singular flap. The size of the flap is double that of the previous to account for the change in area. And then on the left, you can see 5 arms, or sorry, on the right, you can see 5 arms. And one of the interesting things I think about this is that the 3 arms is very simple and quite robust. It doesn't tend to fail out. However, you can assume that if the loss or breakage of a part would be very significant, whereas with 5 arms, you have a bit more resilience to failure, but there is also more to go wrong. So that needs to be looked at there. Thank you very much for watching, and I believe that now is time for questions.